I just want to remind you that we did resonance structures already in our previous class, where we learned that resonance structures are just movement of electrons within the structure. Yeah? But today we will be learning about our acid base. Now, acid base, as the name has indicated over many times for us, acid in general, when you think about it, is a proton donor. So what is the basic acid that you think of? HCl, H2SO4, and so on and so forth. All of those acids give away a proton, and that is when we know that it is an acid, right? So that is what we have learned so far in our general chemistry books. So continuing from here, acid is something that is a proton donor, while base is something that will accept that proton. However, this definition does not fit for every compound that we are going to look at. What we are going to look at is the Lewis definitions. Now, Lewis definitions fit everyone. Lewis base is an electron donor. So what is a base? Think about a bed. Base is an electron donor. Always remember that. Now, how do you know which molecule will donate and which molecule will not? And so this is when you will have to memorize who are the electron donors. Everything that can have excess electrons, and we did this yesterday also, electrons in excess or a negative charge. That is your electron donor, followed by a lone pair, followed by pi electrons. So this is something that we already discussed. Who is the electron-rich molecule? In acid-base reactions, the base donates the electrons while the acid accepts the electron. So in an acid-base reaction, the movement of electrons is from the base to the acid. So from one molecule to the other molecule. That is the difference between a resonance and an acid-base reaction. Acid-base reactions are very fast, and we will see that if electron donation and an electron acceptance can occur, it will occur even in presence of other mechanisms and reactions also. So let's look at a couple of our molecules here. Now down the lane, I will stop writing lone pairs. But you need to remember how many lone pairs any atom has. For acid-base reaction, I will show you an equilibrium reaction. For acid-base reactions, we will always assume a left side and a right-hand side. We cannot say that these are the starting materials and these are the products. In some of the books, it is mentioned like that, but in general, we must always say that this is the left-hand side and this is the right-hand side. Why? Because there is a dynamic equilibrium. On one of these sides, yes, the reaction will go in the forward direction, and I'll show you those as well. Let's look at these three examples. In example A, I have this molecule and I have this molecule. If I had followed the Bronsted-Lowry concept, I would say, oh, this has a hydrogen and this has a hydrogen. Both of them should be the hydrogen donor. Both of them should be the acid. But that is not how you must look at it. You must look at the electron donor. Now looking at both of these, the hydrogen is attached to a chlorine and the hydrogen is attached to a nitrogen. 99% your electron acceptor will be a proton. But there are a few exceptions, and we will look at those also. So whenever I ask you to look at a electron acceptor or the most acidic atom, try to look out for a proton. So among these two, both of them have a hydrogen, but who will be the electron donor? So how many bonds the nitrogen is making? It is making its 3 bonds. And nitrogen also has 1 lone pair. What about chlorine? Chlorine is making its 1 bond and it has 3 lone pairs. The question is, and if you remember yesterday's lecture, are these lone pairs, can these lone pairs delocalize or can be given away?
No.
No.
No, we cannot give away these lone pairs. And so the only lone pairs available for donation are from this nitrogen. So among these two, this is the base, this is the basic atom. This is the acid and this is the acidic atom. Let's look at this example. Very similar to this, we have a HCl here. Both of these compounds have a proton here. But let's look at who will actually be able to donate electrons. Among the chlorine and the oxygen, it will be the oxygen which will become your electron donor, because we cannot use the lone pairs from chlorine. So this will become your base and oxygen will be your basic atom. This is going to be your acid and hydrogen here is going to be your acidic atom. You need to be able to recognize your acidic and basic sites, just like you can recognize your electron donating, electron rich and electron poor sites. That's what you should be able to do. Tell me in C, out of these two, first of all, does this look like a reasonable structure to you, all of you?
Yes.
Yes, right, because all of the octets are complete. I did not show the lone pairs, but that's fine. You can live with that. What about this molecule? How many carbons are in this molecule?
4.
3.
1, 2, 3, 4.
4.
Yes, so 1, 2, 3, and a 4. What about this oxygen? Is the octet of this oxygen complete?
It's negative.
It is not, and hence it has those excess electrons causing it the O negative. Now looking at these two situations. Of course, there are carbon and hydrogens everywhere. I did not draw them out. But among all these hydrogens and all these hydrogens, who will be more acidic and why, and who will be more basic and why?
C4H9O will be a base because it's more likely to donate.
Exactly. Very good. Because of the negative charge, this oxygen will be your electron donor and the most basic atom in both of these. Even though the lone pairs are available, lone pairs are a little less strength of electron donation. So this is your base, this is your acid, and either of these hydrogens can be your acidic hydrogen. Let's do one more. And this is where you will use your information or knowledge of counter ions. Looking at both of these structures, I have hydrogens here, I have hydrogens here, I have hydrogen here also. And I know that most of the times acidic atom will be a hydrogen. So I will still focus on my electron donor. Among all of these, who is going to be my strongest electron donor? Taylor. Taylor Medlin, are you here?
Yes.
Okay, please help me with this. Now I'm looking at this hydrogen and I'm looking at this hydrogen. In this structure, I only have one hydrogen. And in this structure, I have two hydrogens, right? Do you want to look at the acidity first or the basicity first?
The acid.
Okay. So out of these two hydrogens, which one do you think is more acidic?
The one on the OH.
Very good. So among these two hydrogens, this hydrogen is more acidic. Now the question is this hydrogen even more acidic than this hydrogen? So let's look at that, Taylor. There is a sodium ion, there's an oxide, and then there is a hydrogen. I want you to remember your counter ion effects. What will be present on this oxygen? I know there are two lone pairs present on this oxygen, How many lone pairs are present on this oxygen, Taylor?
2.
Okay. And are you sure that's all?
Yes.
So remember, and thank you, Taylor. Every one of you, you need to remember this. The moment you have a metal ion, you have to remember that metal ion will have a positive charge. And anything next to that metal ion will get a negative charge on it. So not just two, this oxygen will have extra electrons on it. So you have this oxygen with the hydrogen and you have this oxygen with the hydrogen. Which out of these oxygens can donate electrons better than the other?
NaOH.
Salome Blackwell, are you here?
Yes, ma'am.
Are you able to understand or recognize which is the most electron donating oxygen?
Yes, ma'am.
Which one is it?
The one with the OH.
Both of them are OH.
I mean, with the Na, the one with the Na.
The one with the negative charge. Okay? Right. Thank you, Salome. So whenever you are looking and you are asked for your acid-base reactions, you must, all of you, must always first thing identify your base and your acid, and then highlight or mark the sites. What does that mean? You should know which atom is going to attack, which atom is going to be your base, which atom is going to be your acid. Acid, base, base, acid, base, acid. So do you understand these 2 points? The next part of this important topic is how to do the reactions. And that is the third thing that you have to know about. We will be using curved arrows. Now we have already started to look curved arrows, exactly just like in your resonance. When you had resonance, whenever there was electron rich area, the electron rich area will go and start moving. Remember, this is the allylic kind of a location. So you see 2 arrows. Why? Because 2 electrons moved. This was in resonance. Now in your acid base, we will still follow the path that starts from electron rich arrow and end it at the electron poor arrow. Now, most of the time, as I said, your acidic or electron poor atom will be a H molecule or H atom. Okay, and in a few minutes, we will also start to look how will you be able to figure out or spot in a structure which is the most acidic hydrogen. Okay, so there are two arrows that you will have to show. The first arrow okay. Now among these two, which is the electron rich area? Remember, that's the first thing that we have to find out, which is the base, which is the acid. Let's say you did not know where is the what. So this is your electron rich source, and this is your electron poor source. Any questions? Do y'all understand? Why is this the acidic part? Why is this the basic part? So now that you have identified your base, which attacks using its electrons as the negative charge or as the lone pairs or from the pi bonds, whatever is available, what we do is the first step is from that basic atom to the acidic atom. So when the base attacks this acid, the base takes away this proton. What is a proton? A proton is a H positive. It is electron deficient. So what is happening here is that in HA, there are two electrons. Remember, each bond has its two electrons. When the base attacks, it only takes the hydrogen. What happens to the electrons of the hydrogen? They are left behind with the atom which is next to the acidic hydrogen. So here A is the atom next to the most acidic hydrogen in the structure. And so these excess electrons become a negative charge, while the hydrogen is now attached with your conjugate. So what we say here is that the base attacks the acid and base takes away the proton, or it says that we can also say that the base has abstracted or extracted, or in Luhmann terms, kidnapped the hydrogen from its original molecule. So we say that the acid has now lost its proton. So remember, where does the proton comes from? It comes from the acid. Why? Because the proton has to leave behind its own electrons. And so this loss of proton will also accompany the breaking up of the proton and the atom next to it. So that is going to be our second arrow. So our first arrow is the abstraction of this hydrogen. The second arrow shows the breaking of the bond and all of the electrons from the bond going to this atom which is next to it. Okay. So now the electrons belong to A. Looking back at all the examples that we have done, let's try to do this. So we have already identified our base and acid. We have highlighted sites. We will now write our two reaction arrows. Okay, I'm going to use my pencil. What is the first step? The base attacks the acidic hydrogen. That is my first step. The bond breaks and all of the atoms are now with the atom next to this hydrogen. So what has happened? The N with all the 3 hydrogens on it has procured or abstracted or extracted out or kidnapped another hydrogen. From where? From the acid. And what is left behind? This chloride. What does this chloride have? This chloride also has the excess electrons which the hydrogen left behind. So we are going to leave a negative charge here. What about this nitrogen? The lone pairs of the nitrogen are now lost. They are now lost to make a new bond with hydrogen. And so this nitrogen has a positive charge. Among all of this, on your left-hand side, what is the overall charge? 0. What is the overall charge in your right-hand side? It is still a 0. Okay. What about the next one? This is my base. This is my acid. I'm going to abstract it out. And I'm going to show my bond here. My second arrow will be like this. Can everybody see this? Any questions so far? So my OH, which is my base, I'm going to draw it out first. Both the hydrogens and then one of these acidic hydrogens also on it. Plus, what is left here? One chloride. Okay. This oxygen usually makes only 2 bonds. One of the lone pair electrons are now lost, making the bond with hydrogen. So it has lost its electrons. It has only 1 lone pair and a positive charge. Overall neutral, overall neutral. With this part, again, this is my base. One of these hydrogens, it doesn't matter, can be my acid, my first step, my second step. I hope all of you are drawing it out because this is also part of your practice. So I'm going to draw out my base first with my O and a H. Where does this H come from? The acidic H. And this OH negative. Now I want to draw your attention. Overall, this side was a negative. Overall, this side is still a negative. Okay. Let's do this last one here. This is my base. This is my acid. I'm going to attack it. And then there is this bond next to my hydrogen. I will give all the electrons to this oxygen or whatever the atom next to it would be. And I will draw my base first. So I drew my OH. Remember, my counter ion is going to behave very specially, or counter ions or spectator ions. They're just part of the molecules. They are not actually participating. And I'll show you what will happen to this sodium ion. So one of the OH will belong from here, and the acidic hydrogen will be right here. What is left? This oxygen is left. The rest of the molecule is left. And because my hydrogen left this oxygen with both the electrons, this will be having a negative charge. Within the system, my sodium ion will also be floating, and it will see that it can no longer make an ionic bond with water because water is now with this molecule because it is a neutral molecule. But it can make, and it will make, an ionic bond with formal charges with this oxygen. Overall neutral, overall neutral. Okay. So once we have drawn these arrows, it will help us see the products as well. Okay. So the atom which your leaving hydrogen or acidic hydrogen is leaving must have the excess electrons on it. Okay. So when the attacking electrons make the new bond with hydrogen, the basic atom will no longer have these excess electrons on them. So if it was a neutral atom, it will become a positive. If it was a negatively charged atom, it will then become a neutral atom. So since two electrons are moving, electrons move from here to here, electrons move from here to here, we have to show two arrows. Any questions so far? Now, just like you recognize your acid and base, you now have to recognize your conjugate acid and conjugate base. On your left-hand side, we write base and acid or acid on base. On your right-hand side, we write our conjugate acid and conjugate base. So what does that even mean? This is a base, and we wrote the base first, remember, because that's the one that the hydrogen took out. That took out the hydrogen. So this base generates a corresponding conjugate acid. This base generates a corresponding acid. This base generates a corresponding acid. This base has generated a corresponding acid. So I usually write my base here first, and then I give the extra hydrogen to it. Another way, and that is the right way to figure out your conjugate acid and conjugate base, is among these two, who has the more acidic hydrogen? That will be the acid or conjugate acid. Or among these two, where is the excess of electrons? That would be my conjugate base. So if I compare these two, this nitrogen has lost its lone pair. And in fact, it has some excess hydrogens on it, making them very acidic. So this structure is going to be my conjugate acid. This structure, by elimination, should be conjugate base. But don't just take my word for it. There are excess of electrons on it, and hence this is definitely a base. What kind of a base? A conjugate base. Who does not understand this part? Okay, very good. Among these two, this has excess hydrogens or acidic part on it. This is my conjugate acid. This has excess electrons. This is my conjugate base. Among these two, both are oxygens, but this oxygen only has lone pairs. This oxygen has both the lone pairs and the negative charge. So this is going to be my conjugate base. This is going to be my conjugate acid. Among these two, Sydney, are you here?
Yes, I am.
Okay, Sydney, help me. Among these two, which of these two is going to be my conjugate acid?
The OH, the H2O, right?
Very good. And why?
Because it has a OH.
Okay, so H hydrogens are here also. But how did I distinguish between these two? That this is more acidic and this is more basic. How did I figure that out?
By the the hydrogens, right?
So this oxygen has excess of electrons on it. So this molecule will become the conjugate base. Among these two, both, if you look back here, similar example, this oxygen has lone pairs. This oxygen has its lone pairs and the extra lone pairs here. Okay, so who will be a better donor of electrons? This oxygen. And hence, among these two, this will be your conjugate base. Is that good, Sydney?
Yes, that makes sense. So
Okay,
it has to
great.
do with which one is most likely to um, donate electrons, and whichever one is most likely would be the conjugate base.
Yes, and I know this is a too much. This is a lot actually to take in. That's why I had suggested all of you to start reading this chapter during the weekend. But
I have a question.
go ahead, Sydney.
So the base acid and the conjugate base, like this reaction, was on the PO H2. So
Hold on, Sydney. I could not hear what you said after.
wait, never mind. I just
No,
didn't
please go
correct
ahead.
it.
I'm sorry, I did not hear your
I
question.
was just saying. Oh, I was just saying. I think this was on the. Can you hear me?
Yes, now I can hear you.
Oh, I was saying. I think this was on the practice learning assignment that was due today. I was just saying. I don't think I did it correctly. If this is what you wanted us to do, but
Okay, don't worry about that. Don't worry about that. But I want all of us to just remember this sequence, because you see these examples and then you see all this done here. I just followed this sequence. And we all need to remember this, that you will need a lot of practice recognizing both your acids and your base. Within the same reaction, you need to be able to figure this out. Okay? Now, I just told you that most of the time, your electron acceptor will be a proton. But there are a few exceptions. Are you all able to see my screen? So
yeah.
for most of the
Yes.
reactions, and okay, thank you. For most of the time, your acid-base reactions will give you a conjugate acid and a conjugate base. That is what usually is the case. However, remembering your module 1, where we have learned some exceptions to octet rule, we will see that borane and sp2 carbons, they are electron poor. They are so electron poor that even hydrogens cannot compete in front of them. What is the octet rule? The octet rule states that in the valence shell, there have to be 8 electrons. But when you look at borane, it only has 6 valence electrons. So among both of these, this molecule is severely electron deficient. And this is where it fulfills the definitions given by Lewis, which only depicts about electrons and nothing about hydrogens. So if you look at this structure, what we get is attack from your base, the Lewis base, the lone pairs attack. And instead of getting 2 arrows, we only get 1 arrow. But what has happened here? We get what is known as a acid-base complex, or a addition complex, or a addendum complex. Okay, why do we call it a complex? Within the same molecule, you will have opposite charges. Of course, overall neutral, overall neutral. But because of the valence deficiency, the deficiency of these electrons, we see that there is formation of acid-base complex and not a conjugate acid or a conjugate base. Similarly, if you look at this particular carbon, this carbon has 6 valence electrons also. Okay, the octet of this carbon is not complete. And so electron poor, even though there are hydrogens are only missing, or they will miss only 1 electron. But this carbon is missing 2 electrons. So compared to hydrogens, this carbon is more electron poor. Whoever is more electron poor will be more acidic. So among these two, this is your Lewis acid, this is your Lewis base. Where are your indications? So this is your basic atom, while this is your acidic atom. If you look at our reaction, the first step is the only step that you will see, attack of electrons to the electron poor area. Now here also I wanted to indicate overall positive charge. Overall a positive charge. Okay. Any questions? Now there is a definition that I want all of you to see here. Carbon is electron poor. Electron poor, electron loving, and hence we label it as a electrophile. Whereas nitrogen is electron rich. It has a lot of electrons on it. It is seeking the nucleus. What is in the nucleus? A nucleus is protons and neutrons. Overall, it is a positive charge. So the electron rich area always seeks the nucleus. And hence electron rich molecules are nucleus loving or nucleophiles. I want all of you to know this term because we are going to use this term several times now. Okay. Now this is just another reminder of how you are going to figure out what is what. Looking at this structure, if you have to identify this as an acid or a base, what will you identify this molecule as? Anyone?
The base.
It is a base. And why?
Because of the negative formal charge.
Negative charge here. Very good. What about this one? Larian Clausel, are you here? Or am I saying your name right? Okay. This pink structure, what would you label this as?
An acid.
Very good. And why?
Because of the positive charge.
Very good. So this positive charge is making it electron poor. Very good. Thank you, Narayan. Iana, are you here?
Yes.
Okay. Iana, help me. Is this molecule considered acid or will it be considered as a base?
I think it would be an acid.
Very good. And why?
I believe because excess H's. I don't know if I'm saying that right.
So it has a H, which is next to a electron spread. So all the electrons from this hydrogen are being pulled away to this oxygen, and hence making this hydrogen electron poor. Okay, very good, very good. And then, thank you, all of you. This molecule, it is acidic here because the oxygen is pulling the electrons from the hydrogen. However, look at the nitrogen. and the donor ability of this nitrogen. Even though there are hydrogens next to nitrogen, we do not usually say that the hydrogen of a nitrogen is acidic. We definitely say that the hydrogen of oxygen is acidic, but not as much as a hydrogen on a nitrogen. So what is going on? And this is what we are going to learn in our next few slides. We will learn how to figure out whether a molecule is considered as acidic or basic and why. And this will also help us predict our reaction in the forward direction. So let's do this. So this is a subtopic that I will cover in the part on how to predict your equilibrium. So this is the fifth part that we should be looking at. How to predict the direction of your reaction, of your acid-base reaction. So if you remember all these equilibrium signs that I made, the left-hand side and the right-hand side are in a dynamic condition, but at least one of these sides is more favorable. Okay. So looking at a chemical reaction, we need to be able to figure out whether or not new materials will form. Okay. This is done by a general chemistry rule. What is the general chemistry rule that all of you have already studied, which indicates that the reaction will go? A strong acid should react with a strong base. And that is the only time that a reaction will go in the forward direction, or any reaction will go and make new products, or the equilibrium of the reaction will be bent towards the right hand side. When you start out with strong acids, you will end up with a weak acid. When you have a strong base, you will end up with a weak base. So strong acid and a strong base are required for a reaction to go in the forward direction, or to make something new, or in the right hand side direction. How will you know that in a given equation? And how would you get an equation? Let's say that I give you two structures and I will ask you whether or not their reaction will go in the forward direction. You will first figure out among those two, which is the base, which is the acid. Then you will highlight the sites of the reactive atoms. Then you will show me the reaction arrows. Then you will label them as conjugate acid and conjugate base. Then you will know, depending on which is your weaker acid, which is your stronger acid. So let's say that if I have this equation that I have to look out for, I will just compare the strengths of these acids. That is one way to look at it. This is known as a quantitative analysis. Quantitative analysis. How is this done? By using pKa values. Now, I'm not sure how many of you remember this. What is a pKa value? Now, pKa values are derived and indicate what is the strength of the acid. Okay. Now, usually when an acid dissociates, it forms these products, and we figure out the dissociation constant of that acid. Now, nothing of this sort is important. You don't even have to memorize pKa's. I just want to give you a quick refresher on what a pKa value is. Now, this Ka value is usually a very, very, very big number. Can you imagine if you have 1 milliliter of hydrochloric acid and you dissolve it in water? How many protons or H positive ions or hydronium ions will be generated? Millions and millions. So this is a few 100,000 big number. So we always take a log of that value to get that number in a reasonable range. So for example, if you look at this table, the pKa values range in a number that we can actually use. Water has a pKa value of 15.7, while alcohols have a pKa value of 16. Amines have a pKa value of 38. So the smaller the pKa value, the stronger the acid will be. And the stronger the acid is, the weaker its conjugate base will be. Now, this is a very interesting thing that all of you need to remember. If you look at the sulfuric acid, this is H2SO4. The hydrogen on this sulfuric acid are making this molecule very, very acidic. In this table, sulfuric acid is the most strongest acid with a pKa value of -9. If you compare -9 and 1.74 with the negative values, which is a smaller number, the H2SO4. And so the smaller pKa value means strong acidic value. When the sulfuric acid loses this hydrogen, right? It loses this hydrogen. Now it is electron rich at this site. Among these two, this is the acid and this is the corresponding conjugate base. An acid always generates a conjugate base. A base always generates a conjugate acid. So if you are seeing a strongest acid, its conjugate base will be the weakest base ever. Any questions so far? Now, this is a very good pKa table. You don't have to memorize this, but in general, you must know that your alkanes, remember, we have looked at alkanes in module 2 also. Your plain simple alkanes are the weakest acid. The hydrogen does not want to leave the carbon. And so the pKa value is so high, it's 50. Very, very high pKa value, very, very weak acid. But interestingly, the conjugate base of an alkane is the strongest base. It is very, very, very reactive. Why? Because it wants to get another hydrogen very quickly so that it can go back to its stable nature. Remember, all chemical reactions occur so that the stability can be achieved. So first thing that we can look at is the pKa values, based on pKa values. And if you look back at the general equation from the general chemistry, the strong acid will have a lower pKa value, which means it will be more reactive, while in your resulting structures, your pK value should be high, which will indicate that it is more stable. Only more reactive will make something new. Now we say that the reaction can go in the forward direction. Any questions? So let's look at this example. First of all, if we are not given the pKa values, how will you figure out which is your acid and which is your base? among all of these structures, the hydrogens on the oxygen are going to be more acidic. Why? Because oxygen is pulling away its electrons, making it more protic. That case is not here with carbon. So this hydrogen is your most acidic hydrogen. This is going to be your acid. Among both these molecules, this oxygen has excess of electrons, and hence this is going to be your base or the basic site. And this is proved by pKa values also. 9.9 is lower while 16 is a higher number. And we have seen low pKa value indicates high acidic strength, right? So this is definitely your acid. This is definitely your base. Any questions? Any questions? Okay. Now, let's look at our next step. The electron rich goes and attacks or abstracts out your hydrogen. The second arrow breaks the bond and gives all the electrons to this oxygen. So to this oxygen gets the extra electrons. While this molecule right here gets the hydrogen. Okay, so this hydrogen now belongs to the base right here. So we have done our reactions, arrows, as well as we have figured out what is the pK values. And let's say the pK values are given to you. This is your conjugate base. Why? Because of the excess electrons. This is your conjugate acid. Why? Because now it has this acidic hydrogen on it. So this is our conjugate base and this is our conjugate acid. Low pKa and high pKa. Now you don't have to compare among these two. What you need to compare is your starting acid and your generated acid. You don't have to worry about the base and the conjugate base now. Only compare the pKa value of your starting material and the pKa value of your conjugate acid. Who can tell me if this reaction will proceed forward or not? Kara Weston. Kara Weston, are you here?
Yeah, I'm here.
Okay, so do you remember what I just said? That lower pKa value means more reactive and higher pKa value means less reactive or more stable. So among these two, acid and conjugate acid, who has the higher pKa value?
The 16.
Yes. And who will be the weaker acid?
The one on the, I don't know, honestly.
Again, look at this. Higher pKa means more stability, less reactive, and weak. Right?
Yeah.
So now tell me, your pK value is 16. Compare this to the pK value of 9.9. Who among these two will have a higher pK value? I can see my background. Do you have another device where the Zoom is on?
I have my computer on right now.
And your phone also?
No, it's not on my phone right now.
Okay, because I could hear a backlight, but that's fine. Now I don't. Yes. Oh, now I do. Never mind. So Kira, whenever you will have a higher pKa value, your acid will be less reactive or the weaker acid? So your starting material and this is your resulting acid. Who is the weaker acid?
The 16.
Yes. So will this reaction go in the forward direction or it will not go at all?
It would go in the forward direction.
It will go in the forward direction. Thank you, Kiera. And thank you for your patience also.
You're welcome.
Any questions from anyone? Do you all understand why this reaction will go in the forward direction? So for some of the chemical reactions, you might be given a pKa value. Okay, when pKa base and the pKa acid will have similar reaction, similar pKa's, your equilibrium will go in the forward direction. Okay, when this number will be smaller than the resulting conjugate acids number. So for all cases, you will have to label up to conjugate acid and conjugate base. Then you will figure out based on pKa's whether your reaction or which acid, what is your acid, what is your conjugate acid, and then you can compare those. Okay. So for this reaction, you can see something like this. Overall reaction goes in this direction. So your equilibrium sign can appear like this. Okay. So based on the predictions, we say that reaction goes in the forward direction or the right-hand side direction while it is making something new. So this is by using your pKa values. A second thing that we do is we use prediction by qualitative analysis. When we do qualitative analysis, we are just making comparisons. And the most important of the comparisons is by checking stability of bases. How do base stabilizes? This is where your resonance will also help you. The stability or stabilization of the negative charge or lone pair. Okay, let's say that I have a reaction A plus B, acid and a base, making a conjugate acid and a conjugate base. So when I have to compare my stability of the bases, I have labeled my acids, I have labeled my bases, conjugate acids and bases, and I have to compare the bases. I will only look at the bases. I will completely ignore my acids at that point. Okay. Let's look at the structure or chemical reactions right here. And for your benefit, I'm drawing the OH as a bond. I would usually write it as a OH. So if you want and if it helps you, you can actually spread the atoms out. Okay, let's do this acid-base reaction. First of all, I'm going to label which is my acid, which is my base. Let's say I have this. I know there are hydrogens here. I know there are hydrogens here. But which hydrogen is going to be more acidic? I'm not sure. Let me look at my donor now. I know that there are these two lone pairs here. I know that there are these two lone pairs plus a negative charge. Why the negative charge? Because of this counter ion. And so I know this molecule with a negative charge is going to be my basic atom, and this molecule will be my base, making this as my acid. Among all the hydrogens that are possible here, this is going to be my acidic site. Any questions so far? Okay, so next I'm going to do my reactions. The base, the electron rich attacks the electron poor. That is my first step. The bond breaks, gives all the electrons to oxygen. And then I'm going to draw my base first, OH, with this extra H. And I'm going to draw all of this part. Why this part? My H is gone now. And what will be the special thing on this oxygen? The hydrogen left, and it left both the electrons for this atom. What about this sodium ion? The sodium ion will float around and find its way to this charged molecule. So I now have to label my conjugate acid and conjugate base. I know this is my acid, this is my base. Looking at these two structures, this is the electron rich portion. This is the electron poor portion comparatively. So remember, acid bases are always a comparative term. Some days when water is acid, there are some days when water can also act as your base. It will depend on which reagent it is attacking with. So now I'm going to look at my base stability. How do we look at the stability of the base? The easiest thing to look while you're looking for the stability of the base is which structure among this. So I'm not going to pay attention to this. I'm not going to pay attention to this. I will only worry about these two. Among the structures, who will have more stabilization? Among the base and the conjugate base, who has more spread of electrons? Now, spread of electrons can be in form of resonance, it can be in form of delocalization, and there are several other methods by which spread of electrons can be seen. And it should be unhindered. There should not be any breaks in between. So if you look at both of these structures, this oxygen with the negative charge on it, this oxygen with a negative charge on it, and spread of electrons around it, who out of these two will be more stable?
The conjugate base.
The conjugate base. Very good. The conjugate base is resonance stabilized. When something is stabilized, will it be reactive or non-reactive? It will be the non-reactive. Very good. Non-reactive means it will be weak. And what does that indicate for us? It does indicate that from a strong base, we should generate a weak base. From a relatively strong base, we are generating a relatively weak base. So will this reaction go in the forward direction? It will go in the forward direction. Why? Because a weak base is being generated. Because our conjugate base is stabilized. Does this make sense to all of you? Okay.
Yes, sir.
Okay, good. Now, the next part under this topic, stability of bases, I will want all of us to learn how to recognize base. If you're given a couple of bases, you should be able to identify which will be the strongest base, which will be the weaker base. So there are three identifications. The first is who has the higher electron donation ability. Again, negative charge, lone pair, 5. That's what the indication is. The second is polarizability. What does this mean? It means who can accept the spread of electrons on the atom. So the smaller atom will not spread the electrons better on it, but a bigger atom can spread the electron on it better. So this is a very simple question that we look at. Okay. And I'm not drawing the dynamic, the equilibriums. Let's say I have these two reactions, same alkyl groups, but instead of oxygen, I now have a sulfur. And I'm using some base. I don't know what. I'm going to grab these hydrogens and I'm going to generate my conjugate bases. Among oxygen and sulfur, if you look in the periodic table, I wish I had my periodic table on me. But if you look in the periodic table, oxygen and sulfur, they are in the same column. Who is smaller? Oxygen. Sulfur is larger. Who can see or accommodate the spread of electrons better on it? The larger atom. And we just saw whoever can spread the electrons better will be the more stable. More stable means weaker. And so among oxygen and sulfur, the O negative will be a stronger base, while S negative will be a weaker base. Do you see what comparison did I do with the atom size? So always remember, if your atom is smaller in size with a negative charge on it, it will have stronger basic properties. Similarly, if you look at carbon, nitrogen, oxygen, fluorine, the carbon with a negative charge will be the strongest base. If you remember, we just saw our pKa values. Right? We have a C negative and then we have an N negative. C is the smaller atom, N is a larger atom, and oxygen, oops, my bad. Sorry, I didn't want to bring it here. And so oxygen is a larger atom than nitrogen also. Okay, Anna, I saw what you said, okay? And the third indication of a strong base is there is more bulk on the atom. What does that mean? So for example, if I have a OH, usually how do I get an OH? From sodium hydroxide and all that. And if I have the same oxygen, but instead of a hydrogen, I now have a bulky alkyl group on it. What is the alkyl group doing? The alkyl groups are having a plus I effect. So if you remember induction is when you have movement of electrons, either it's a push or a pull. So they are pushing their electrons towards the oxygen. Here, hydrogen has no effect, neither push nor pull. But the alkyls here are pushing their electrons towards this oxygen, making this oxygen what? Electron richer than this oxygen. Okay. Any questions on how do we recognize our base? Okay. So let's quickly do a poll here. So I will give you 4 choices. And I wish I would write them somewhere. You will have CH3, CH2 negative. You will also have CH3, NH2, NH negative. You will have CH3O negative, and then you will have a PR negative. Can you all see my periodic table now?
Yes.
Okay, good. So, do you want to see those structures again? I'm going to launch the poll now. So who among the following is the most basic of them all? You just have to choose one. Remember, most basic will be most reactive. It will not be most stable. It will not be most low energy. It will be most reactive. And when you think about base, we are thinking about electrons. But for the most unstable structure, you are thinking about electrons which are not spread out, which is very vigorous and ready to attack so that it can form something more stable. Remember, that's the whole point of doing any chemical reaction, that you want stability. Few more seconds. So base also follows periodic trends. Okay, 10 more seconds. 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay. And so most of you have answered B, which is CH3NH negative. Okay. However, among all of these choices, the most basic of them all will be the one where the negative charge is on the carbon. So if you look back at our periodic table, as the size of carbon, nitrogen, oxygen, they are in the same row. And so their sizes are very similar. If you look at a bromide, which is a halogen, and a bigger halogen for that matter of fact, the electronegative element or the atom will spread the electrons on it better, stabilizing this structure. On the other hand, if you look at carbon, it will not be very happy to lose its hydrogen. It wants to quickly, reactively, vigorously want to get another hydrogen so it can become its stable molecule. Okay? And I just told you a few minutes ago that carbon with a negative charge is the most basic, then N negative, then O negative. Okay, so this is something that all of you need to remember. The basicity trend. Okay, the basicity
Dr.
trend.
Verma,
Go ahead, Michaela.
so the first one was the correct answer?
The first, CH3, CH2
Okay.
negative, is the correct answer. Yes. So among these, this is the most basic of them all. Okay.
So moving right of the periodic table, you would get more acidic, and moving left, you would get more basic.
Exactly. So they are opposite, right? The trends are opposite. If something is basic, it will be weakly acidic. If something acidic, it will be weakly basic, right? So they are opposite trends. That's a good observation, Michaela, yes. So when we do the qualitative analysis, stability of bases is what we look at first. And you need to recognize the stability by the spread of electrons. And the other things that we recognize bases are these three things. Moving on, the second thing that we can look at or compare when we are doing qualitative analysis is the strength of acid. So there's stability of bases, and now we will compare the strengths of acid. And we do this by using what is known as the ARIO. Okay. What is ARIO? When you look at the complete definitions, A is the atom or how the atom is located in the periodic table. Because of that bond polarity and acid strength, it can indicate how much acidity is involved with that atom. So strength of acids, which is done by the ARIO. We first look at the atom, then look at the resonance, then look at the induction. Atom, location in the periodic table. So let me draw my, O, F, S. Now looking at this small periodic table, carbon, nitrogen, oxygen, fluorine, and I'm not listing out those inert gases. We just observed that basicity increases when we move towards the left of the periodic table. One of the first things that you must remember is acidity will increase as the electronegativity increases. Okay. So electronegativity of the atom. Why? Because if a hydrogen is attached to a carbon, the electron pull is not there, not even there. What about nitrogen, hydrogen, oxygen, and then a fluorine? So among all of these, we can visually see that the hydrogen next to the most electronegative element will be the one which will lose its electrons. So the dipole is strongest at this site, and hence all the electrons from the hydrogen have been pulled down. The second thing that we look at in the atom's location is the size. And we just saw the size effect. As you go down, the acidity increases. If this is more stable, its corresponding starting acid would be very reactive. If this is okay in strength, not very stable, its starting acid would be also not very reactive, but okay reactive kind. So size down the lane will be more important than electronegativity. So En just depicts electronegativity. So in this case, we know that this is most electronegative because this hydrogen will be most acidic. If you have to compare between hydrogen for carbon, hydrogen for nitrogen, hydrogen for oxygen. However, if you have to compare fluorine, bromine, and iodine, as you go down, this will now, even though fluorine is the most electronegative element, it is this hydrogen that will be the most acidic. Oops, this should be the most acidic hydrogen. So size is more important than just electronegativity because the unshared electrons, once this becomes I negative, there was a base here, let's say, base with hydrogen, this conjugate base will be more stabilized because of its large size. The electron, the unshared electrons, will be spread over better on the large orbitals. So within the column, the size will win. In the same period, the electronegativity is more important. But if you have to compare electronegativity and size, it is definitely the size that is going to win. Any questions? So if we look back at this little example that we did, where we had an oxygen with a sulfur and oxygen on a hydrogen and a sulfur on a hydrogen, out of these two, which will be more acidic? The sulfur's hydrogen. Why? Because oxygen with the hydrogen and sulfur with the hydrogen. Out of these two, which will be more acidic? The hydrogen on the sulfur will be more acidic. So that is where your atom comes to play. The second thing after atom is resonance. And resonance, we have already seen, is the movement of electrons via the vacant orbitals and unshared orbitals. So again, who can stabilize the negative charge? Let's jump to our slideshow. So if you look at these two structures, if you look at this oxygen and if you look at this oxygen, in these two separate chemical reactions, where is the acid and where is the base? In both of these cases, the acidic hydrogen is right here, whereas the basic atom is right here. In this case also, the acidic atom is right here and the basic atom is right here. How do we know that? Because We will see in a minute how the resonance, it's not here, here. Resonance is stabilizing this conjugate base while there is no resonance present here. So out of these two reactions, this reaction will be faster. Why? Because it has a more stable conjugate base and hence its starting acid must be very, very reactive. More stronger acid than the acid right here. And so this reaction would be faster. Why? Because the conjugate base has been stabilized by the resonance. Okay. On the other hand, the next part is induction. So I'm not going to go into details of resonance again because I spent the whole class yesterday on resonance. So if you look at all of these structures, you can look at the corresponding conjugate bases and figure out which of these is the stronger acid. If we compare ethanol and its conjugate base, and if we compare acetic acid and its conjugate base, we just have to compare who is more stable. This one is more stable because of the resonance stabilization, and hence the starting acetic or its corresponding acid will be more unstable or more reactive, as we say. So the next third part is induction. When you have induction, induction also is when you can stabilize the formal charges. Remember, induction is just a push or pull of electrons along sigma bonds. When I say sigma bonds, the first bond that is formed between any two atoms. More electronegative elements have a more stronger pull towards them. Alkyls, on the other hand, push out electrons. Okay? So remember, electron withdrawing groups are like electronegative elements which are pulling your electrons. Electron releasing groups or electron donating groups, as we say, are the ones that push electrons towards the atom. The last part is when you have orbitals. But let's look at a few examples before we go there. If you look at this CH3, this CH, this carbon, and this carbon, it's localized at the same location. But look at the pK values. Who has the smallest pK value? This has the smallest pK value, and hence its acid strength will be super high. Why is that? It is because at the same carbon, you are being pulled with how many chlorines? 3 chlorines are even pulling this hydrogen's electrons. So this pull is being experienced by how many elements? There is no pull here at all. Only 1, 2, and then 3. So not only that, if you look at these two, 1, 2, 3, 1, 2, among A and B, who do you think will have a smaller pKa value? This
A.
one. Smaller pK value, which is more acidic. It is B. Why? Because this F is closer to this acidic hydrogen, whereas this F is 3 carbons away. This is only 2 carbons away. See that? and this is only one carbon away. So among all of these, C is the most acidic, followed by B, followed by A. Do you understand this, Nelson?
Yes.
Okay. Any questions from anyone else at this point? Okay, the last trend that we need to look at are the orbitals. And why orbitals? Orbitals are looked at towards the end because usually we don't do more reactions with them, but there's one important reaction that we will look at so many times that you will memorize it. Again, with orbitals, you have to look at stabilization. Stabilization by the S character. Now, in sp hybridized carbons or atoms, 50% S character is there. When I say S character, which is the spherical orbital, and then there is this P character also. However, if you look at sp3 or sp2, that spherical nature is lost. But in sp, the negative charges can be stabilized if it is held close to the atom's nucleus. So all the electrons, instead of being spread out like in directions, in sp, there is a spread of electrons experienced. So because of this spherical symmetrical shape and more S spherical character helps the stabilization of the negative charge on a sp atom. What does that mean? It means that if you compare all of these conjugate bases from a sp carbon hydrogen, from a sp2 carbon hydrogen, and a sp3 carbon hydrogen, you will see that this is the most stable structure, most stabilization, weakest base. On the other hand, with this is going to be the least stable. And so the corresponding acids for a stable is going to be reactive or unstable. The corresponding acid for the least stable will be very stable or unreactive. So the whole point is that you need to recognize where is the stability, which side is the reactivity or less stability. If you are generating stable materials, the starting materials definitely want to react and make that new product. Okay, I'm going to end this part right here, but I strongly encourage all of you to please go back and look at all of these tomorrow. We will be looking at some more of this part. I'll go over a few exceptions and we will do a few examples before we move on to the nomenclature tomorrow. But please make sure that you read through this part again and practice more questions. There are many sample questions that I have placed on Brightspace as well. Make sure you do all the skill builders and the questions at the back of the chapter also.